Hello, ladies and gentlemen. Today I'll be presenting you path planning for LiDAR equipped UGV in building inspection. I'm Ying. I'll be representing my team to present you our research. The content of our presentation will be including introduction, literature review, aim and objective, methodology, as well as result and discussion. As our topic evolve around building inspection, so we'll be stating the main limitation and challenges currently on the building inspections, so which is safety, productivity, and accuracy. So regarding safety, there are risks of workers working at height as well as hazardous environments. So for the productivity, a building inspection require long inspection cycles and high demand for human resource, as well as the accuracy, which will be misjudgments in inspection. That's why we opt for advanced method and technology in the building inspection. So currently we use 3D reconstruction for building inspections. And there are two major technologies in the 3D reconstruction, which is laser scanning based and photogrammetry based. So photogrammetry, it is based on image as well as structure from motion and multi-view stereo algorithm. It's low cost, easy to deploy, but it's sensitive to lighting and texture. Whereas for the laser scanning, it's a very direct method in capturing the 3D point. It is high accuracy, depending on sensor, robust in complex scenes, but usually come with expensive hardware and software. So after we obtain the 3D reconstructed model, or we call it as point cloud data, we can perform scan versus beam process, which is a digital inspection process that compare the as-built point cloud data with the as-designed beam model. So usually this is used for detecting deviations. So you can see from figure 2 where the point cloud is aligned with the beam model, and then the deviation is showing in a different color range, where red, there's the major deviations. So usually the workflow will be laser scanning of the site, pre-processing, and semi-automated, automated comparison, and deviation analysis. So the challenges that we face is we think that the quality of the point cloud data is very important, as well as the scene complexity, which will be the major challenges in the scan versus beam process. So ongoing, we did some reviews on the robots with LiDARs. So we realized that there has been many scan planning research that has been extensively conducted on TLS, which is the figure 4, which enable high precision data collection, but the mobile LiDAR system remains limited. So for this kind of low-cost LiDAR system, since there are many different kind of LiDAR with different brand, so we think that the data quality and scanning performance remains uncertain and requires systematic evaluations. So that's why together with this evaluation, we also wanted to provide a customizable and automated path planning algorithm to support this efficient and complete data acquisition. So for the research gap of this research, we think that there's a need to evaluate the low-cost LiDAR accuracies to determine their reliability for collecting precise point cloud data. Or for the second one, there's a need for path planning approach that prioritizes LiDAR scan coverage and data accuracy in building settings. So our aim is to evaluate the 3D point cloud reconstruction capability of UGV equipped with low-cost LiDAR sensors and optimize their data collection path to improve the completeness and accuracy of point cloud data. So our objective, the first one will be evaluate the accuracy and performance of low-cost LiDAR sensors. The second one will be to develop and implement a 3D path optimization algorithm. And the third one will be identify and validate the optimal scanning path through simulations. So this is our methodology workflow. So the major concept of this methodology is to first assess the LiDAR accuracy, since there are so many different kind of LiDAR available in the market. So we plan case study in two scenes. One is the structured scene and one is the unstructured scene. So for the structured scenes, we think that the major factors that affecting the accuracy will be the distance. So we plan it in different distance and then obtain the scanning results. And for the unstructured scene, we select a random path and a planned path to see how it performs in a complex scenario and obtain the accuracy. So after validations, we select different kind of path planning algorithms. And then for the model preprocessing, this will be the input map for the algorithms. So the final algorithm that we select is the genetic algorithm and A-star, and we optimize the path and process the data. So we wanted the path to have a shorter path length and more points number, and we'll give it a scoring and we'll get the resulting path. So this is the result of the case study 1, which is on the LiDAR accuracy assessment. So for this one is the structured scene, whereas this one is the unstructured scene. So for the structured scene, you can see the point cloud from 2, 4, 6, and 8 meter. So for the 8 meter, it's very sparse, whereas for the 2 meter, it shows sharp edges, and it has LiDAR error, which even achieved the LOA 30 accuracy level of accuracies. But because of the placement of the LiDAR, so it is occluded in some way. Whereas for the unstructured scene, so we have selected a column to evaluate their accuracy. So you can see in the picture, this is the TLS, and it shows clear boundary of the entire column. Whereas for the LiDAR, it shows thick point cloud. We think it's because of the registration error from the SLAM algorithm because it's in a complex scene. So after obtaining the assessment result, so we did the path planning using different case studies. So first we need to convert the beam model to FBX and then to PCD, which is in the point cloud format. So the beam model that we choose is an entire floor with classrooms and corridors. And we did calculate the feasible map for the corridor. And then you can set up the LiDAR parameters according to the LiDAR that you selected. So we set it up ours in this way. So following on, we'll be using the genetic algorithm and the ISARC for the point cloud simulations. So you can see that the number of points in the point cloud is in an increasing manner with the increment of the generation. And at the meantime, we will need to ensure that the path length didn't increase exponentially together because we will need to get a balanced efficiency and point cloud coverage with the path length versus data gain. And in this algorithm, we have set a scoring, which is 80% of point cloud quantity plus 20% of path for it to optimize. So the final result point cloud is shown in this figure 12. So in conclusion, we have proposed a scan-oriented path planning method for LiDAR UGV, and we have validated the impact of scanning path on point cloud quality, and we have also developed a hybrid algorithm which combines the GA and ISARC that successfully optimized path coverage, and we have also demonstrated adaptability to beam model. So in the future, we wanted to add more point cloud quality into the path planning algorithm. So maybe it will not only improve completeness, but also find a balance between different kind of point cloud quality, or maybe even tailored to your needs. So other than that, I also wanted to introduce some related research with the building inspection. So first is for the scan versus beam. So this is what I introduced in the introduction. In this study, we obtained the raw point cloud data from construction site. And as you know, construction site is very noisy, so we need to do some noise removal before the scan versus beam. And afterwards, we did the point cloud registration with the entire site to detect the deviations and aid in the construction project. So if you're interested, you can build this with this title. So this is another research related to building inspection, but it's on crack detection. And it doesn't use LiDAR, it uses RGB and thermal imaging. So first it's about data acquisition, and second we propose an image alignment method using two-step registration, which this is very important because the accuracy of the registration will affect the semantic segmentation result afterwards. And usually when you are acquiring RGB and IR image, they won't be in the same pixel width and length, so that's why it is very difficult to align them in pixel perfect accuracy. And then after image fusion, so we developed this data set with different kind of image channel, and then we put it into the neural network for training and evaluation. So this is the result of the crack detection. So we can detect better with the IR image. And this is the references that we use. And thank you. That's all of my presentation. So if you have any questions, so you can email me. Thank you for listening.